you took an image. Okay? So in an image, for one image, what is the problem if you use the image directly? You can directly use the images, right? There is no problem. But if suppose you want to further go beyond the images, the problem is that you may have to extract out features from these images. Features means edges. Edge is one sort of a feature. Then texture features. Because if you take one pixel, if both the pixels are green, for example, forest and plantation. If you take the satellite image of both, if you take pixel wise, both of them will look alike, will look same because both of them are having almost the same color. But what distinguishes them is their pattern. One is having a random pattern, other one is having an organized pattern. So for understanding pattern, taking one element or one pixel will not help you, but you have to take that neighborhood. And you have to compute certain measures based on that neighborhood. That is where we call it, the patterns that we have to take. So that patterns can be the edges, it can be other texture features, anything. So that said, now comes how you can extract out these features from your image. So I think most of you are from electronics background and all of you know convolution way better than me. So here convolution basically means that you are convolving, in simple terms, you have an image here and you have some filters. So you can see that you are taking the weighted sum of that neighborhood to get the values here. For example, the 4 that you are getting here is the weighted sum of this neighborhood with respect to the kernel weights. So why we are doing like this? Because we want to, this is the kernel. When I convolve this image with the kernel, this is what I am getting. So this is one such feature. If I use another kernel, what I will get is another feature. So can you tell me one feature, one kernel, which you can use to extract out the edges? See, edges are something where I told you already the frequency will be varied. So if I throw something like this, so this is one, I am not sure if it is. Okay. Fine. See, this is one patch of an image. So if I have values here, say certain values, say all the values are same. So all the values are same. What does it mean? There is no edge in this patch. But the moment I write say 255, 255, 255, here say 0, 0, 0, 0, 0, 0, that means there is an edge. There is a difference in pixel values. So if I use a kernel, say for example 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, what it will do? If I overlay this with this, 1 into 255 plus 1 into 255 plus 1 into 255 minus 0 into 1 minus 0 into 1 minus 0. So that means he is taking the difference between this row and this row. So that means I can say that if there is an edge at this position by using this kernel, if I get 0 value here means there is no edge. Why? Here also 255, here also 255. If I subtract this row and this row, there is no edge. So this I can use for detecting horizontal, the edges in this direction. That's the same way if I use another kernel 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. I can detect the edges in this direction because it will subtract this. So this way I can have different types of such. So this is an example of a high pass filter image because it will detect edges. What if I will use a kernel where Here all the kernel values are say 1 by 9, 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 1 by 9. These are the kernel weights. So what will happen? The value at pixel position 1 plus into 1 by 9 plus the value at this position into 1 by 9 plus the value at this position into 1 by 9 plus the value at this position into 1 by 9. All these are added together. So that means I can take the 1 by 9 out in common. So that means this plus 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 this divided by 9. So what is that average of this neighborhood? So that means the new value that I am getting here will be the average of this neighborhood. So the next one, if I place the kernel here, the average of this neighborhood will be the value. So I am averaging out the value. When you average out the value, what will happen? One student in our class, suppose a student is having very high mark, all the other students are having low marks. If we average the marks, what will happen? The difference between them will get reduced. So that means if there is someone in the class whose marks are very different from others, we are treating them as a noise and we are trying to bring them almost in similar lines with others. If I replace this value with the average of this value, and if this value is very different from the other values, of course I can say that I am trying to reduce the difference. So when I reduce the difference, what happens to the frequency? Frequency will reduce. The spatial frequency will reduce. Spatial frequency is a change in pixel values over x and y. But as I am reducing the values, what will happen? The frequency will reduce. So that means if I use an averaging filter, the frequency is a low pass filter. It will not allow features to pass through. That means I can either extract out features using a high pass filter, low pass filter, or whatever filter I want, and I get these features. So this is convolution. You can use this filter or many filters to convert this image, and you will get here different values. So this is called one feature. Okay, and this, if you repeat, you will get another feature. So these are called feature maps. Then you convert, and you can easily see here. Then we see here. So each of these gives rise to one feature. So can you now correlate this with the bases? I told you in Fourier transform the bases are computed using Fourier. So you got Fourier image number 1 as the base, Fourier image number 2 as another base, Fourier image number 3 as another base. Same way, if you use multiple filters, you are getting features which will actually form as the base of this particular image. So you are actually synthesizing, another set of bases using image processing techniques. That means if I will put one sort of a filter value here, I will get one feature, another filter value here, I will get another feature. So that means I can use different filters to get different feature values. So this is where So I have almost like 10 minutes. So I'll just this is what I wanted to say is that so I'm not sure if I am confusing you, but just you can correlate this with the Fourier basis. Like in Fourier, the bases were computed based on Fourier transforms. You get a lot of bases. Here the bases are computed based on your features. So you can see here, you have an image. So you have a lot of bases. So if you go back, these are your bases, right? This is feature number 1, this is feature number 2, many features. So these are your filters. This filter convolve upon this will produce this feature. This filter convolve upon this will produce this feature. So you have multiple features. You have dictionaries. You have sparse codes. Now think in reverse direction. This image was decomposed into these components by using these filters. So that means if you think reverse, these are the basis of this particular image. So you can reconstruct this image from these features. So that is where we say that this is called convolutional sparse coding, or you can convolve to get features which forms the basis. So since I have to close, I will just say that you can use artificial neural network to learn those filters. I told you, as you change the filter, the feature changes. Okay, so as you change the filter, feature changes. So you are here learning filters. That means you are actually learning which feature is the best to represent your image or your set of data. So that means you are neither relying on Fourier, you are neither relying on wavelet. You can learn wavelet, Fourier or something else based on whichever is the best suited to represent your data. So that means given a set of data, you can use machine learning approaches to learn these bases. So how are you learning the basis? Most of you may have heard about deep learning and machine learning. What's the basic difference between deep learning and machine learning? In machine learning, machine treats everything as features. For example, if you give a child an orange, how he will say that it's an orange when we were kids? Based on the color, based on its shape, based on its weight, you can say whether it is an orange or a jackfruit. So same way, so the features of the orange are color, texture, shape and all these things. Same way, you can have different data objects can have different features. So for a pixel, for a spectrum, what are its features? It is its values in different bands. Now each pixel, if you take one pixel of a hyperspectral image, it's having values in different bands. So all those values are its features. So those features you can give to the machine, and machine will do something based on that feature. But can you extract, like I told you can extract the edges from images, can the machine themselves learn these bases of features? That is where we call it deep learning. Deep learning means the feature space itself is learned by the machine. That, you can see that here, this is just a neural network. You are giving a spectra as the input, you are getting the spectra as the output. But what here the machine is learning is a different representation. Here you can see we had 5 inputs. That means 5 features to represent the spectra. But here you have only 2. So that means the machine is somehow learning some feature which can better represent this spectra. So this is like a learned feature space. So your machine is learning at different levels, different features. Like sometimes it may be edges, sometimes it may be object parts, different things it is learning. So for this we use something like a convolution neural network. The idea is that it will simulate convolution. I leave it to you to just understand how it is simulating convolution. Here you flatten the image. So you are flattening the image. Okay, flattening the image means you have 2-dimensional image, you converted it to 1 dimension. Now this is your kernel. This is your kernel. So your idea is that you have to convolve this kernel over this, right? That means this part into this one, this part into this one, this part into this one, plus this part into this one. The sum of all this should be the first convolution result. So you can see here, this is your first convolution result. How it is happening? This is connected to this is connected to this, and this is connected to this is connected to this. You are combining all of them together to get this one. It will be more clear here. You can see here this filter, when you are convolving with this one, what is happening? You just resize it. So first, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11. So you can see here, if you consider the first neighborhood, first, second, third. So first, second, third is connected to this. Now fourth is not connected because fourth is not coming in this 3 by 3 neighborhood. So you can see that like this, if you connect it, you can simulate the convolution. So I hope all of you are understanding this. You can see here, this neighborhood if you take, this is connected to 3. Same way this neighborhood, it's connected to this one. So this is simulating convolution. So that is why we call it as convolution neural network. And What are these different colors? You can see these different colors are the weights of your kernel, and these weights are nothing but the weights connecting these values to this one, and they are shared, and that is how a shared weight neural network can simulate convolution, and that means it can generate features. You can generate the features. You are getting the features. Now you can, instead of using original features, you can use the learned features for classifying your object or whatever. If you, instead of the cat image, if you use spectra, you can do that. So this is, the machine learning part of that. And now you can also use this concept for super resolving your images, where you use, the dictionaries and sparse codes as the basis, learned basis. Since because of limitation of time, I am stopping here. I don't want to confuse a lot. So see, the idea is that you can have learned basis using machine learning. So machine learning is a generalization of all these transforms. You have Fourier, you have wavelet, you have different. You can have textures, you can have edges. But can we use machine learning to learn this? So convolution neural network can simulate convolution and can generate features, so that so I'll just go through the last part. These are some of our works which you can go through. These are published in IEEE Transactions, so you can go through these works if you are interested. And papers I have already given there. Then you have spatial resolution, spectral resolution, all these things, even multimodal data fusion. These are a part of different projects that we are involved in. And these are some of the projects that we do. One is, how you can use this for ISRO. We are doing, the hyperspectral scanner on board of Chandrayaan 2 and Chandrayaan 1. We are using it for mineral mapping, lunar mapping of minerals. We also have a core research land which we use for spatial data warehousing. You have data from multiple sources. I told you these are signals, these are 2D signals, but the moment you have them from multiple sources, you have to combine them together to take some decisions. Also, we have another project from ISRO where we try to use this multi-model data fusion and type of approaches. We have some consultancy projects, and also we have some projects with the Indian Army. These are some of the publications. That said, I wind up this talk. Thank you so much for listening and hearing me for this. Any of you, if you want to work on these things or explore more, please feel free to contact me. I'll be sharing my mail ID and phone number. You can collect it from sir. Okay, and just one more thing. I have had a classroom, Google Classroom. So all of you will be added to that classroom. In that, I had some basic hands-on for image processing, hyperspectral data processing, especially. But we couldn't cover that. But you can see it's actually well documented. So you can go through it and learn by yourself. Sir will be adding you to that Google Classroom. I have added him already to the classroom, so you can have a hands-on there. Thank you.